welcome everyone to our first New Mexico first workshop, and Project Neo has graciously offered to host this tonight, and we'll be learning a little bit today about the Romi and use of that in FRC for developing programming skills. And so with that, I'd like to turn it over to Randy Rankin and Eric Liefeld, and I'll let you guys take over from there, if that sounds good.
Sounds good. Let me figure out how to share a screen here. All
right, there we go.
Beautiful. So my name is Eric Liefeld. I'm a systems and software mentor for Project Neo Robotics. And we're going to talk about building a competent FRC software team. So we are going to talk about the Romi. We'll get there eventually. But I wanted to kind of give you just a little bit of background. As Randy said, some teams were interested in how to put together a software team for FRC robotics. And that's something that we don't quite have completely mastered, but something we've been working on for a while. Next slide. So we are, for those of us who don't know us, we are Project Neo Robotics. We are the FRC team in Las Cruces, New Mexico. So we're open to all area high schools and home schools. We like to say in our marketing materials that no experience is necessary. And that's kind of the approach that we take for teaching software as well, is that we take kids as they are and hopefully put them in a position to do good things with FRC robotics programming. My background, I have a very old bachelor's degree in computer science from the 1980s, and a minor in mathematics. I ran a Unix IT shop at New Mexico State University for a number of years, which gave me some really good experience in understanding Unix systems, understanding IP networking. Both of those, it turns out, are really useful because they are endemic to our robots. I worked in the corporate world as a systems engineer for Sun Microsystems. Other good experience that exposed me to things like the birth of the Java programming language. I got to watch the internet kind of get born and grow up. And then I've been running my own business for the last 30 years as a freelance technology ghostwriter for a wide variety of clients. My rookie mentor year was 2017. You can go ahead and go to the next slide. Well, I'll get to that in a second. So we'll talk about, challenges for FRC software. We'll talk about our aspirations. Where would we like to be? We'll talk about realities. We'll talk about the approach that Project Neo has been taking for the last several years, and then we'll get into the Romi and do a little demo at the end of the talk. So I included this because my rookie mentor year was kind of an adventure. I got recruited in the middle of the build season, and it was the year of first Steamworks. I don't know how many folks remember first Steamworks, but it was probably the most baroque, complex FRC game yet devised. We had two different kinds of game pieces. We had human players literally in the middle of the field on a giant apparatus. We had gears that had to be lifted up into that apparatus in order to spin propellers. We had little balls that we had to launch into gigantic goals. And at the end of the game, we had to lift our robots up by a special rope that we provided. So it was just a fantastically complex game. Like I said, I showed up in the middle of the build season. We had two student programmers who did not speak the same language metaphorically, and we're talking past each other. We were coding in C++ using an iterative programming model. I don't know why there's an A on the end of the model. Ignore that. most of our programming effort that season was focused on a very expensive and sophisticated vision system. We got down to like the last week of build season, and we realized that nobody had thought about how that vision system was going to be integrated into our robot. So the vision system worked. As we started to try to get it integrated, one of the other mentors managed to crash the computer that was running on it, and we ended up losing the entire thing. So not a great season. When we didn't understand, fundamental things like network tables. We didn't understand the smart dashboard. We got to competition. We had also managed to ignore the fact that there was a mandatory software update. So we spent, a large part of the first day of competition trying to get our system updated. We missed all of our practice matches. We literally drove our robot for the very first time in our first competition match, which I do not recommend as a strategy. And we tried to program autonomous, in the practice area. So this is kind of FRC worst practices. This is where I started and what I've been trying to overcome and forget for the last 7 years. Okay. And the big lesson is that FRC software is hard. It's really hard. The robot environment is complex. You've got a couple kinds of networking. You've got all kinds of configuration issues. You've got everything from the RoboRio to speed controllers that need to be configured to the radio. The programming environment is extremely powerful and very sophisticated, but also really complex. You've got to pick a language. That's kind of a big decision for a lot of teams. Where do we start? Are we going to program in C++ or Java? I think there's a few teams actually still using LabVIEW. Visual Studio Code is the integrated development environment, IDE, that's used for FIRST. Very, very powerful tool, but you've got to learn how to use it. WPI-lib is the software library that we all use. Also fantastically powerful, but also complex. There's lots of things you need to understand about how to use it. And then you've got to be able to integrate in third-party tools and libraries. Lots of us are using CAN bus-based speed controllers as an example. And all of the CAN bus-based libraries have been moved out of WPI-lib. So that's something you have to understand how to integrate in. You've got to be able to just contend with the software environment, installing the National Instrument tools, the FRC driver station, getting your game controllers to work. Then you've got to be able to understand smart dashboard. How do I get information back off the robot to let me know what's going on? And that's sort of before you even get into talking about advanced object-oriented programming and so on. So this stuff is hard. We've looked around, and I'm sure lots of other folks have too. What are the big teams doing? What are our aspirations? If we're going to compete in these games, what do we need to be doing? Most of the big teams are using command-based programming, which is something that's available through WPI-lib. They're using controls to be able to do precise things. If you've done any robot work, you probably understand that robots don't necessarily turn precisely, don't necessarily drive straight. And we've got to have software that lets us do those things. Most of the big teams are using automation, whether just in autonomous or in their actual gameplay. They're able to pick up game pieces by just running into them. They're able to score automatically, right? More precisely and more reliably than a human player can score. Lots of teams are using advanced drive configurations, things like swerve drive. That's a whole programming challenge in and of itself, as we learned last year. There are folks who are identifying objects with vision systems, with April tags, which we now have on the field as of last year for the first time. And there are teams using neural networks to do identification of game pieces of the field, and other things. Last year, with the introduction of April tags, we literally have the ability to localize our robot on the field, to know precisely where we are on the field and what our orientation is, if we can figure out how to do it. And there, of course, are lots of teams using path planning, trajectories, and automation of very complex sequences in the autonomous period. So those are the things we'd like to be able to do. What's our reality? Well, you know, we typically get freshmen who have, if we're lucky, a little bit of block programming, maybe a little bit of Arduino. Yeah. You know, what we really need is students who are ready to program kind of at the college level. So there's a huge mismatch here in what we're trying to do and where we are. And our experienced programmers, you know, keep graduating if we're lucky. And like any robot team, you know, we don't have a robot until late in the build season. Programming, you know, if we do it wrong, is literally the last thing that happens. And there's never enough time. So what I've been thinking about over the years is, how do we teach this? We literally can't start with teaching programming like we would typically teach programming. Like, okay, pick a language, how do we write a hello world program? And so a typical programming learning curve just will not work for us. Okay. So this is kind of our approach, which, you know, I won't say is intentional. It's kind of something that's evolved. We tend to teach robot programming top down, which is to say we throw kids off the deep end. We start with object-oriented programming or object-oriented programming concepts. That seems to be something that kids can understand rather directly. We then move into looking at command-based code structure from WPI-lib. And we look at, you know, sort of where things are done in that code structure. When do you need a subsystem? When do you need a subsystem method? When do you need a command? How do you tie a command to a button? And we sort of let the IDE, we let VS Code essentially teach the programming language, because it does such a good job of auto-completing. You know, you start to type a programming command and it finishes your sentence for you for the most part. We also try to work as a real software development team. Now, this is something that students won't encounter in their, even if they're a CS major, until they're taking a 300 level college course. You know, typically they aren't taught to work together. Well, we have to work together. So we pretend to be a real software development team. Everybody gets an account on our little IT systems here, and everybody gets a GitHub account. So we are, you know, beyond the Romi programming, which we'll talk about in a minute, we are all working on the same code tree in GitHub, and trying not to clobber each other and learning hard lessons sometimes. Yeah. This adds a lot of complexity, which isn't necessarily desirable. But we find it's totally worth it, because it teaches us to communicate and it teaches us to cooperate as we build that code tree. We teach software and systems. We aren't just teaching programming. Early on, I had a student or two who were fantastic programmers, but if you gave them a laptop that wasn't completely set up, they froze. They didn't know what to do. We want our kids to be able to react and improvise, and, oh gee, I don't have the right drivers on here, I'll go fix that. You know, we want them to have all of that experience. So we teach IP networking, both wired and wireless, because those are germane to the robot. We teach a lot of configuration as far as computers, networks, radios, speed controllers, because we encounter those situations in competition if we have to replace a speed controller for whatever reason. the new one's got to be configured to match the old one. And we need to be able to do that quickly, and not miss our next match. Okay. So, you may be thinking, I don't really need to build a software team. I got this one really smart kid and he's going to save our bacon this year. And we've been there before. But I think this can be a trap, because it represents, a single point of failure. If you have just one kid who understands the programming environment, what happens if they go away in the middle of build season? Or what happens if they get sick? Or what happens if they accidentally delete their program, and then decide not to come back? So there's lots of things that can go wrong with that model. It seems simple and it's tempting to go that way, but we'd like everybody to have the skill, if we can. Okay. So let's talk about the Romi a little bit. We got excited about this during the pandemic, which is kind of when the Romi was born. What's nice about it is it lets you do FRC programming, real FRC programming, without having to have an FRC robot. So you can do this in the off season, you can do this in the build season before you have a robot. You can literally, use the FRC programming environment, start developing your code, and then move over to a real robot when you're ready. They're small scale, they're relatively tiny. They aren't going to hurt anybody, so we don't feel bad about turning them over to students. We try to have each student programming on their own Romi, but sometimes we have to pair them up depending on how many kids we've got going through the program. They are inexpensive. They cost about $130 for the basic Romi kit from Pololu, and they cost you need to add a Raspberry Pi to that, and that's essentially the computer. So you end up about $200. Like I said, they are fully compatible with the FRC programming environment. They're supported by WPI-lib, VS Code, all the programming languages, and so on. And they're surprisingly useful. They have all the basic components of a robot. They've got a right drive and a left drive. They've got encoders. They have an IMU, a gyroscope, an inertial measurement unit. And you can do some pretty advanced things with them. So this is how they come as a kit. That's kind of another helpful aspect, is that you can have the kids assemble them at least once. You can take them apart again if you want. And that's useful for figuring out which students are able to actually follow instructions and end up with something that works. The Romi itself, if you see the sort of black board that's in the middle of the red plastic carrier there, that's the Romi controller board. It is basically an Arduino, but it's got some specialized things on it to talk to their parts and pieces. And it comes with its motors and encoders and all the rest of it. And then a Raspberry Pi, even just a simple Raspberry Pi 3, flips over upside down and plugs into that assembly. I don't know if I can get this close enough to the camera. So you're looking at the bottom of a Raspberry Pi there. And that is the computer, that's the brains of the operation. It runs an image that is provided by FIRST, which is nice. It's actually a thing supported by them. It used to be the image they used for vision processing on the Raspberry Pi. It's now called WPI Live Pi, and it too is running Linux. And you can do other things. You can actually still do vision processing on it if you want. And it provides not only computational horsepower, but the Raspberry Pi provides wireless networking for the Romi itself, and USB and other things like that. So if you're used to programming in a typical FRC model, you're used to the RoboRio. So let's talk about differences between them. On the RoboRio, your code is compiled in VS Code for the ARM processor that is on the RoboRio. Your code is then downloaded to the Robo Rio over your radio's network, and then it's run on the Robo Rio. The driver station connects to the Robo Rio using the unique address for the Robo Rio on your little local area network there, which is usually something of the form 10 dot your 4-digit FRC team .2. In contrast, the Romi is a little different. We don't actually download code to it. The code is run on the PC in the FRC robot simulator. And then the simulator communicates with the Romi over a WebSockets interface. So again, the Raspberry Pi is providing a wireless network, and we are sending commands essentially from the PC to the Romi over the WebSockets API. From the computer side, the robot can be driven with the FRC simulator GUI. That's kind of the natural thing to do. But we can also drive it with the FRC driver station, just like we would a real FRC robot. And we'll go through both of those in our demo in a minute. Okay. So what can we do with the Romi? Is it just a toy? Well, yeah, it's kind of toy-like. But the cool thing is that we can do some rather advanced things. As I mentioned, I like it because we can introduce students to the whole programming environment and the whole FRC software tool set and coding principles. Out of the box, we can drive it. There's a piece of code that is in VS Code. All you have to do is basically create a new project using that code as your starting point, build it, download it to the Romi, and you can drive the thing right out of the box. So that's very handy. It gives the students a sense of accomplishment, and they can see, that their assembly has worked, and they can go through and say, okay, what's making this thing tick? How does it work? Understanding program structure, specifically WPI-lib programming structure, is a big part of our learning curve. So the Romi lets us do that. We can output values from the Romi back to the smart dashboard or the shuffleboard. So for example, we can output encoder values from the drive motors on the Romi back to the shuffleboard, and we'll show how to do that in a minute. We can play with the shuffleboard further. One of the things that we're working on as a team is getting better at having smart dashboard configurations for testing and smart dashboard configurations for competition. So we can play with all of that without involving a real FRC robot. And we can get good at it so that when the real build season comes along, we're ready to do that. Believe it or not, we can add PID controls. So we can do real controls programming with the Romi. We can set it up so that we have a command, for instance, to turn to a specific angle. And we can have a PID controller that's reading the gyroscope on the Romi and making sure and adjusting so that we actually are turning to that exact angle. We can have a command to drive straight at a certain speed, for example. And we again can have a PID controller that's driving the Romi straight, even if the Romi doesn't drive straight naturally out of the box. Did we lose something?
No, it's going to matter to them.
Okay. Something that I was frankly astounded that you can do is that you can actually characterize the Romi using SysID, which is an FRC tool. And you can then use something like Path Planner to drive complex trajectories. So if any of you were participating back in the 2021 season, when it was all remote and we had various obstacle courses to run, you can do all of that with the Romi, which is very, very cool. If you get that skill mastered, then you're in a really good position for building a useful and complex autonomous for your robot for competition. There are some LEDs, so we can do some status signaling on the Romi. We're going to try to build some little LED strips to add on to the Romi, because we do have some GPIO pins that we can drive things like LED strings from. You can add a camera. There's a kind of a hilarious little Raspberry Pi camera that's just, you know, a teeny tiny thing on a ribbon cable. We've tried that, it works. You could do vision programming on the Raspberry Pi, you know, to detect objects or center on a target or something of that nature. So yeah, it's a toy, but it's a pretty cool toy. And there's lots of, you know, extensible things that you can do with it. Come on, there goes. So at this point, I will introduce two of our software and systems teams members. Liam Gazeli, who's to my right, and Sam Iorio, who is to his right. Hello. And these guys, last year was your first year on the team, is that right?
Yes.
So they're both softwares here at Arrowhead College High School. You guys had what? A little bit of, you had some Arduino experience.
I had like nothing, I'm not gonna lie.
Okay, so again, not atypical to have, you know, a little bit of programming experience, maybe a little bit of block programming experience. And by the end of the season, these guys are very capable. They're able to throw together a complex object-oriented program, debug it, make it work, roll with the punches. And there's a link, by the way, if anyone wants to jot it down. That's the kit for the Romi. So at this point, we will switch over to Liam's computer. Do that.
So this is the Romi web interface. Typically, as Eric was talking about, you would have a team IP notations. That would be like for our team 11.64.10.11.64.2. But in this case, the Romi just follows the 10.0.0.2, no matter what team you're on. And this web interface do quite a few things here. Notably, there's the IMU calibration. So this will calibrate the gyroscope to be a little bit more accurate. And then if you have stuff like vision or need to change network settings for some reason, then you can do all that. And there's some various example programs, application stuff that you can do there as well. As far as driving it goes, you can
Actually, why don't you go back there just a second. So again, what's happening here is that the Romi, so this is live. He's actually talking to this Romi that's sitting on the table. And the Romi is creating its own Wi-Fi network. And it has a little tiny web server on it, in addition to everything else. So he's attached to that with his browser, and he's able to interrogate all these parts and pieces of the Romi. What's nice about this, if you've ever worked with a Raspberry Pi, you'll know that it's very easy to clobber yourself. It's very easy to screw up and overwrite your little micro SD card. This tool makes it so that most of the time when you're using it, the micro SD code is in read-only mode. If you need to change something, you can actually set that on the browser, and it helps keep you safe as you make those changes. Sorry, go ahead.
Yeah, so right up here, there's the read-only and writable, and that also helps if the Romi was to lose power or something, then hopefully then there wouldn't be like corrupt memory. Over in VS Code, you can create an example program, and that would be, I go to the command palette, that's Control-Shift-P, and then I can make a new project. And I can select a template, or actually an example program, and we use Java. So I'll select that, and then I can search for Romi. And now that will create an example program. Now I've already done that, and I believe you would like to click enable desktop support, which will allow you to use FRP driver station. That will also show here in a second. But since I already have one created, I'm just going to run it. Again, that was Control-Shift-P and simulate robot code. So this is going to run it in Java. And then that will create the WebSocket and open up the simulation. So from here in the simulation, we have various joysticks that can drag and drop those, and I can enable the robots somewhere. Enable button. Oh, I don't know.
My demo screen.
Yeah, she's kill off the simulator. Okay. I'll also close off that is in case that matters. Here it is. Okay. Okay.
Well, this is actually really important. Forcing students to go through the process of making this stuff work is hugely valuable. So that, you know, by the time these guys get to competition, they've done this, you know, 100 times. And when they see a symptom, they know immediately, you know, what to do. They either know what was causing the problem or they know how to work around it. And that kind of experiential learning, you know, I think is just invaluable. And one of the reasons I really like using these tools.
So somewhere, somehow it popped up a robot state, and I have disabled autonomous teleop, and I'll do that in a second, but we also have joysticks over here, and I see our Logitech controller that we have, but it's not assigned to a joystick right now, so I'm going to drag that over to our first joystick slot 0, and then I'm going to enabling, and then Stan should be able to drive that. Beautiful.
So again, this is out of the box functionality. We've not done anything complicated to this code. And that robot's ready to run.
So disabled. That's how you can use the robot simulator, but you can also use
Before we go on, just note that you have all of the modes here that you do in a typical robot program. So clearly in competition, we have a teleoperated mode, we have an autonomous mode. And our code gives us the ability to have a test mode as well. All of those things are accessible through the simulator. And you can test out pieces of your code and get good at using those different parts of the code, all from the simulator without going any further.
And then there's some stuff in here too, where there's Romi gyroscope and built-in accelerator and network table stuff. I haven't messed with that too much. But if I close that and I can open up, actually I'll start that again. Commit the robot code. Now open up driver station. And I'll make sure that this stays open. That way I don't close the network socket. But if I go over to my settings, and once everything opens up, I have my shuffleboard here, and then I also have settings over here. Now, normally this would be routine numbers. It appears to be working right now. I'm not sure why that is, but if you change this to localhost, then that should now be feeding back into that WebSocket that we just created with the robot simulator, and now it should be able to drive everything on here. So if I enable that, beautiful. Now it's not driver station can be a little bit weird sometimes. Not sure why that is, but I'm not seeing values. I can drag and drop some of these out. And it will show us our acceleration, stuff like our angle. And then I can also see our, how far each wheel has driven, which could be useful information, but more so just to show that we can display a lot of information on the dashboard. So these distances here, if I enable that, and can drive it. Go that into for the left and right wheel, and we can.
My sincere apologies.
I didn't say we taught them to drive.
It would be important to mention, we were also our drive team.
That would be a bad thing to mention.
So that's how you can kind of incorporate it with the robot simulator, and then also get it working with your smart dashboard and the driver station. And the code is all roughly the same. If you take a look at code, you know, there's a subsystem for drivetrain or onboard IO systems. To put everything on smart dashboard, I went over to the drivetrain, and on the periodic, I just put some general information, not too much. I was able to get that going fairly easily. And you can change things like how the joystick acts by changing the axis on that the controller uses, and however you would like it to work. I can kind of mess with that.
Anything else?
I think that was it.
Okay, so that's, you know, again, there's a lot of cool stuff that's going on here. When he's driving it with the driver station, and at the same time displaying values back to the shuffleboard or the smart dashboard. You know, that's using network tables, which is this funky network-based database that gives us, you know, basically every object in WPI lib has data associated with it in network tables. So there's a lot of cool stuff going on here, and we're actually able to interrogate the robot and get data back from it. We could, for instance, if we had written a PID controller and we were trying to tune that PID controller, we could use the smart dashboard to input our PIND values to help us tune. And we could do all of that with the Romi, pretty much as the system's already set up. So at any rate, that's why we like it. If anyone's got any questions, we'd be happy to try and answer them.
I guess one quick question, Eric, in terms of I'm assuming we can send out this presentation to the email list for everyone.
Sure.
Okay. And then I guess my question was just in terms of downloading to the robot, and could you go over that process again? Because it was just connecting it up and doing that through wirelessly, right?
Yeah, the Romi, exactly. The Romi itself, it has an Ethernet interface on it. It has a wired interface on it. I mean, you could plug a wired, you know, that's the Raspberry Pi. You could plug a wired cable into it, but then it wouldn't go very far. But it also has a wireless interface on it, so it creates its own wireless network. It is essentially acting as a wireless access point. So when Liam is connecting to it here, that's what he's connecting to. The code in this case is not being downloaded to the Romi. The code is actually running in the simulator on the PC. And what's being sent to the Romi are commands over the WebSockets API. So there's a WebSocket sender and receiver essentially on the computer, on the laptop, and on the Romi, and they're exchanging information back and forth. So we aren't downloading code and running it. We're just sending commands essentially and getting information back from the Romi. And that's different than how the RoboReel works in a real FRC robot. But it's appropriate for something this small because we don't want to burden the Romi with lots of programming tasks because Raspberry Pi is ultimately, limited in what it can do.
Okay,
So-
thank you. That
Answer-
helps.
This is Fred. I have a real quick question. So this network address that the Romi generates, if we have 5 in the room, are they going to generate the same address?
They do, and it's, you can handle that a couple different ways. It's usually not too much of a problem. Last time we had multiples on, it wasn't a problem. We just had to make sure that we were connecting to the right ones. You can also put them in bridging mode and put them on your own local area network, so that you can have them all visible on your local area network. We've not done that, but it's supposed to be a possibility.
And you just can't then overwrite or force a custom address?
You can.
Okay.
Yeah, you can.
So just to clarify, the addresses are all the same, but it's on a different Wi-Fi network. So it might be like Romi 1 or Romi 2 or Romi 3. So all the Romis are still going to be putting out the 10.0.0.2, but you're going to be connected to a different network, so it's going to connect to a different Romi.
Yeah, so you just need to be able to, you need to make sure that you're connecting to your Romi and not your neighbor's Romi. And so that's literally just a different Wi-Fi network. Within that Wi-Fi network, you're assigned the same address, but it doesn't matter because they're on physically, separate Wi-Fi networks.
Got it. Different frequencies,
Yes.
or are they different coded?
Well, they're different Wi-Fi networks. So they're all in the same frequency and that they're all, whatever.
I think
Different
we're-
network name,
Yeah, yes.
Yes, correct. That's it.
which is a different address, I guess, technically, right?
Different address space, yes.
Got it. Yeah, it'd be interesting, how to map all that out in a, because so many of the students, especially me, are visual learners, and if you show it graphically or pictorially, they just go, oh, got it. And then they know where, when they're changing a value, what they're physically altering. So thank you.
Any other questions?
Yeah,
Has anyone else played with these?
I haven't played with it, but I was just going to ask, if you don't have a Romi, could you use the simulator to do something just 2D on there, so you could still get the advantage of practicing programming and seeing some kind of output? We haven't played with that before.
Yeah, that's a great point. The simulator is a thing all by itself. And you can do very sophisticated simulations with it. We have not, but that's something else that is certainly possible.
Okay.
And I've seen teams using the simulator, and there are ways to actually get CAD files in it and a field description in it so that you can actually, you can do a lot of really interesting simulation with it, but we've not gone there yet.
And what I couldn't see is the driver's station. What was being used to move the Romi around the tabletop? Do you have
We have a controller right here.
Just a standard game controller plugged in.
Oh, okay. So I didn't see that. I didn't know if you were using a mouse pad or a separate game controller. Got it.
Yeah, same mechanism, whether you're using the simulator or whether you're using the driver station. It's just a game controller, just like we drive all of our FRC robots.
My favorite history in mind.
Yeah, students learn not to plug USB devices into the Ethernet port as a part of our program.
Very important lesson. I used to do it on the daily, but I'm grown.
Any other questions?
Oh, thanks for sharing this. This is great.
Absolutely. I think it's a really cool way to kind of teach a lot of the framework and help us get a little bit more experience and I like the way you've set that up. So again, thank you very much. I echo Zach with appreciate your time this evening. Eric, would it be okay if I share your email as well? I'm sure if people are going to go try to implement this, they may need a little bit more detailed tutoring or detailed mentoring to kind of get through that. And so if you're willing to do that, I'll send that out with your presentation to the mailing list.
Sure, absolutely.
Excellent. Cool. If there's no other questions, our next so thank you for being our inaugural workshop host. Thank you very much, Project Neo. Good job. Excellent work. So the next one that we're going to host will be on the 23rd of October. And Project Y is going to host a workshop on SolidWorks. And then we'll trade some more lessons learned amongst the teams. So thank you all very much and appreciate your time this evening. And again, thanks again to Project Neo for all your hard work tonight. Great job, guys and gals.
Thank you.
Thank you.
Thank you. Good night.
Thank you.
Good night.